All right, we have wrapped up all other types of FRQs. There are 7 types of FRQs, you remember. We've covered 6 different types, gotten plenty of practice with those for now. So now it's moving on to the last type, type 7, which is area and volume. We are going to be covering these 5 problems throughout this review of it. And our introduction problem will be 2013, number 5. In this case, it is a non-calculator problem. When we are talking about area and volume, we are talking usually about the area of a region bounded by 2 curves. We're talking about the disk method, the washer method. You're talking about volumes of cross sections. So this was from actually our last unit that we covered before we started preparing for the AP exam. So with that, let's go ahead and get started. Here we are given 2 functions, f of x and g of x. One we notice is a parabola that opens up, and the other one is a cosine function. So the first thing I want to note is which function is which in the graph. In the graph, f of x is the bottom function, and g of x is the top function, at least in the interval 0 to 2. All right, for part A it says find the area of R. Well, the area of R, remember, is always the integral of the upper curve minus the lower curve. Now, we know that the upper curve and the lower curve can change places, but in this case, from 0 to 2, from the points of intersection that we have here, they don't change places. G of x is always above and f of x is always below. So the area of region R is just going to be the integral from 0 to 2 of g of x minus f of x dx. Now, I said g of x minus f of x, but notice I wrote out the actual functions. The reason I wrote them out is because this was a non-calculator problem and we are finding the area. So that means we have to go through and evaluate this nasty equation or integral expression. So we need to, in order to evaluate this, we need to take the antiderivative of all this. Well, this part's going to be easy enough, but this part is going to be a bit of a pain, to be honest. Well, before we do that, I'm going to go ahead and distribute the negative here. So we end up with 4 cosine of 1 over 4 pi x and then minus 2x squared plus 6x minus 4 for my integrand. Now, to take the antiderivative, well, the antiderivative of cosine is sine. A lot of students are mixing up the signs of this, the positives and the negatives. So please make sure you're taking the derivative of what you get to see if it matches your integrand here. So the first thing I note is that there is a 4 as a constant, so that's going to go first. So we got 4, and then times the antiderivative of cosine, which is sine. So we're just going to rewrite all of this, sine of 1/4 pi x. And then notice we have an inside part of this. So to deal with that inside, we're going to undo the chain rule in a sense, and if you need to use u substitution on this, you can. But you might be able to think through it without. To undo the chain rule, we actually have to divide by this coefficient here. So really what we'd be doing is multiplying by 4 over pi. And again, we should be taking the derivative of what we get here to make sure it matches that. But before we do that, let's go ahead and finish up the antiderivative. The antiderivative of negative 2x cubed is going to be negative 2/3 x cubed. Sorry, antiderivative of negative 2x squared is negative 2/3 x cubed. The antiderivative of 6x is 3x squared. And the antiderivative of negative 4 is negative 4x. And that's all going to be evaluated from 0 to 2. Now before we go on, let's take the derivative of this to make sure it matches. The derivative, well, all of that, actually before we do that, let's simplify this one step. What I notice is that 4 over pi times 4 is just 16 over pi. So now let's take the derivative of this to see if it matches this. Well, the derivative of this is going to be 16 over pi times cosine of 1/4 pi x, that's good, and then times 1/4 pi. Well, when I multiply this by 1/4 pi, the 1/4 reduces with the 16 to get to 4, and the pi out here reduces with this pi here, and so that goes away altogether there. And then, of course, taking the derivative of this, you end up with 2x squared plus 6x minus 4, so we did that right. Now we're going to go ahead and plug in our upper bound to x and plug in our lower bound to x and subtract them. Please do not be lazy on this. I know a lot of times when we see 0 here, we just think it's going to cancel everything out. It does not always cancel everything out. If this was cosine of 1/4 pi x, it wouldn't cancel out. If this was e to the 1/4 pi x, it wouldn't cancel out. In this case, the sine of 1/4 pi times 0, well, 1/4 pi 0 is 0, and sine of 0 is just 0, so that's all 0. And then all of these polynomial expressions are all 0. So in this particular case, it does go away, but you still need to show the work even if it does go away. So we just need to basically simplify this first big term. The sine of 1/4 pi times 2, well, that's the sine of 1/2 pi, which is 1. So 1 times 16 over pi is 16 over pi. And then 2 cubed times 2 thirds is going to be 16 thirds. 2 squared times 3 is 12, and then 4 times 2 is 8. We'll go ahead and get a common denominator here of 3 on those constants, and then we'll simplify all that, and we end up with 16 over pi minus 4 thirds. That was a long part A. The points for this, you would get 1 point for having the correct integrand. So if you knew it was upper curve minus lower curve, you get the 1 point there. You would get 2 points for the correct antiderivative. Now, I don't know exactly how they would break this down. My guess is you would get 1 point for having the correct antiderivative for the trig function, and then 1 point for having the correct antiderivative for the entire polynomial function. So in all reality, even if you did the trig antiderivative wrong, you'd still get 2 points, one for the integrand and one for the second antiderivative. And then you would get 1 point for your final answer. But again, thinking about simplification, right here, all of this right here, woohoo, woohoo, you do not have to go any farther than this. You do not have to simplify. And you might be making a major mistake going from here to here. So do not put yourself in a position to lose the answer point by just trying to make your answer look pretty. Don't simplify at all. Just leave it like this. It's all numbers. Okay, you might argue, well, sine of something isn't just a number. Yeah, that is just a constant number, so it's okay. There's no variables in this expression, so that is an answer. Leave it like that. Trust me. All right, so for part B now, let's take a look at part B. It says, write, but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 4. So actually, before I go on, I'm going to go ahead and draw the line y equals 4. It's a horizontal line, and notice it's right at the top of right where these two functions intersect. Now we are revolving region R around that line. And so as we revolve it around that line, you're going to get circular cross sections. So that means that this is either going to be the disk method or the washer method. Now in this case, as I revolve both of these curves, you're going to see that there's going to be a gap on the inside. There's going to be a hole inside of it. So that's actually going to be the washer method. And if you remember the washer method, the volume is pi times the integral of the big radius squared minus the little radius squared, and we'll get more into that in a second. But the big question is, what are the two radii? Well, the distance from, remember, the distance from the center of rotation, the axis, to the curve is how big the radius is, because when I revolve this distance is going to be the same as the distance on the other side, and that's what makes the diameter of the circle. Anyways, so the big R is the distance from the axis to the curve that's furthest from the axis, and little r is the distance from the axis to the curve closest to the axis. Now, how do we express these distances? Remember, the radius is always given or always written as the subtraction of the curve and the axis. Now, in this case, the axis is above, so we're going to say that big R is 4 minus f of x. If the axis of rotation was below the curve, then it would be the curve minus the axis. So in this case, it would be f of x minus 4, but the axis is above, so it's 4 minus f of x. And then little r is going to be 4 minus g of x. Now, go ahead, plugging that into our washer method, we would get the integral from 0 to 2 of 4 minus f of x squared minus 4 minus g of x squared dx. And I made a major mistake there because I forgot pi. So there should be a pi out front. And that is a major mistake. That's going to dock me points. Shame on me. Go ahead and fix it though. Okay. Because I want to go through the rationale behind this before we move on, just to make sure we're good with this. Basically what we're doing is we're finding the volume of a cylindrical shape that has a hole in it. Okay, and that's a bad cylinder. Horrible, horrible cylinder. Can't draw very well when it's like this. But I've got a cylinder that looks something like this. Okay, and then I have a hole inside of it. And so the logic behind this is if I can find the volume of the big cylinder, find the volume of that guy, and subtract the volume of that little cylinder that's on the inside, that hole, then I would find the volume of the piece remaining. So this guy is the hole, and this guy is the outer shell, as you would say. And so this is going to be pi times big R squared times h, and this is going to be minus pi times little r squared times h. And so we can put those together because they both have h, and the heights are the same all the way through, and the pi's are the same. So this becomes pi times big R squared minus little r squared, and then times h. And so we can see that in the washer method. Here's your pi, it's a constant, so we just took it out of the integral. Here's your big R squared minus your little r squared, and then your h is dx. That's the thickness of each individual cylinder as you slice these up into an infinite set of cylinders. Anyways, that's the answer. The points for this, you would get 2 points for having the correct integrand. My guess is you would get 1 point for knowing that it's the washer method. So if you had something that had some r squared minus some r squared, you get the 1 point. And the second point would be having the correct radii values here. Okay, so if you flip these wrong, if it said 4 minus g of x squared minus 4 minus f of x squared, you would get 1 point because you knew it was the washer method. And if you had like f of x minus 4 squared and g of x minus 4 squared, you would probably get 1 point because your radii are not correct there. So just be careful with that. All right, looking at part C now. Oh, sorry, you get 1 more point for having the correct limits and the correct constant. What's that mean? That means you have the correct upper and lower bound, and then you had your pi out front. So I would have actually missed a point there. If your pi is on the inside of the integrand, as long as you're multiplying it to both terms, that would also be okay. All right, so for part C it says let the region R be the base of a solid. So I hear that and I'm thinking cross sections. I'm thinking volume of cross sections. For this solid, each cross section, there it is, perpendicular to the x-axis is a square. Write but do not evaluate an integral expression that gives the volume of the solid. So the first thing I notice is that we have perpendicular cross sections to the x-axis. So remember that to find any volume, no matter what, when we're talking about volume using calculus, it's always the integral of the area expression. And you can see it here too. It's the integral of the area. Well, the area is pi r squared. That's the area of a circle. Area of a circle because we were revolving. Here, we're talking about the cross sections being squares. And so it's going to be the integral of the area expression. Now we need to know whether it's in terms of x or in terms of y. Well, it says perpendicular to the x-axis, so it's going to be a in respect to x dx. And that's going to help us look at our limits too, because our limits are going to be x limits, not y limits. So it's going to be from 0 to 2. Those are our x limits. And now the question is, what is the area that we're talking about? Well, we're talking about a square. And it says that the cross section here, the perpendicular cross section, so I'm looking at this from straight above. So I can't see, looking at it from the side, from this view. This is at the very top of each square. So this is looking at the aerial view, if you would. Okay, so this length here of this cross section is actually the base of the square. Okay, so that's the base of our cross section, or it's the base of the square. So I'm going to go ahead and draw a square. Now this is the side view, this is the cross-sectional view, and this is the aerial view. So the length of this square, this distance from this point to this point, is the distance from this point to this point in the graph. Well, how do I figure out that distance? I find that distance by saying the upper curve minus the lower curve. And so that distance would be g of x minus f of x, because g is my cosine curve and then f is my parabolic curve. Now because this is a square, that means the height is the same as the base, and so the height would be g of x minus f of x. And in order to find the area of this, I would just say g of x minus f of x squared. And that's the area of the square. And so all I have to do is plug that in to my integral, or in my integrand. And so the volume is equal to the integral from 0 to 2 of g of x minus f of x squared dx. Some silly things I see here. I see students putting a pi out front. There's no pi. You're so used to the disk and the washer method that you think you got to put the pi there. But there's no pi here because we're talking about square cross sections, not circular cross sections. If it said that the cross sections were semicircles, then you might have a pi there. But these are squares, so there's no pi in squares. Anyways, point values for this. You would get 1 point for the correct integrand, so g of x minus f of x squared, and then 1 point for having the correct limits from 0 to 2. Alright, so there is my example of area volume problems. Now it's your turn. This is the last type, so you only got 4 more FRQs to go. So we just did question number, let's see, which one was that? That was question number 5 of 2013. You now will do question number 2 of 2014. This is a calculator problem, so go ahead and give it a shot. Hopefully you do well on it. Remember to set a timer for 10 minutes and then come back and watch the next video to see how you did.